Hello everyone. Today we're going to work on a flexible body. In this video, I'll show you how to set up the simulation of a cantilever beam. First, add a flexible rectangular beam to the model. You can adjust the geometry of this block, whether it's solid or hollow. In this case, I'm going to use a 0.2 by 0.2 meter solid beam. The material properties can be specified here. For damping, you can model the beams as undamped, proportional, or uniform modal damping. Proportional damping defines the damping as a linear combination of the mass and stiffness. Uniform damping applies a single damping ratio to all vibration modes. In this case, I'll use proportional damping with a stiffness coefficient of 0.05. In the discretization section, you can adjust the number of finite elements in the beam model. Now, let's construct the model. I'll rotate the beam around the y-axis by 90 degrees. Then add a weld joint to represent the fixed wall. Port A and port B of the beam are the coordinates at both ends. In this video, I'm going to go with this setup: a cantilever beam under a concentrated end load. To add a tip load, I'll use the external force and torque block. I'll apply the force in the Z direction and rotate it back by 90 degrees. In this case, I'll use a step input to verify the model by checking its static deflection. I'm going to go with 2000. I'll also add a sensor at the tip to measure its position. It should be placed here at the B port and measure from a follower frame. It should be in meters. Well, I forgot this. Alright, the static deflection of a beam under tip load is given by this equation. I'll use the variables from the file I created to set the beam's properties. So, the static deflection at the tip should be 71.4 millimeters. Alright, for simplification, I'm going to turn gravity off. Now let's see the result. You'll see the beam deforming like this. Now let's check the time response. As you can see, the static deflection at the tip is correct. So how about the deflection at midspan? I'll add a new frame right in the middle of the beam span, like this. Then add another sensor and connect it to this frame. Alright, let's perform the calculation. The theoretical value is 22.3 millimeters. Let's check the simulation result. Let me look at the close-up view. As you can see, the deflection is correct. Well, This flexible body can be simplified into a single degree of freedom mass spring damper model. I'll bring this model here. You can check out my previous video on how to set up this model. Let me organize this. Alright, I'll use the same input signal and use this to compare the results. I'll specify the mass and stiffness of this equivalent model according to these equations. And for the damping, I'll use beta multiplied by the stiffness, just like I set up in the flexible beam. It's 0.05. Alright, let's see the comparison. Let me change their names. The yellow line is coming from a flexible body, and the blue line is the equivalent system. I think it looks good. Let's try applying a harmonic load. I'll add a sine wave to this model. The first natural frequency of a cantilever beam is given by this equation. Rho stands for mass per unit length. So the natural frequency is, sorry, I forgot a constant, 10.3 radians per second. And for the equivalent model, we get 10.49 radians per second. That's pretty close. So I'll use 10.4. All right, let's see the result. As you can see, it's not a perfect match, but it's good enough for an approximation. Actually, we can change the boundary condition of this model. For example, you can set up a base excitation problem by replacing the weld joint with a prismatic joint, like this. I'll place it here, so this joint can move in the vertical direction, and use motion as an input, and change the force actuation to automatically compute. I'll change the unit in the converter to meters. Change the input filtering to second order filtering. Okay, I'll shut the force off by gain block. And scale this one down. All right, here we go. You'll see the fixed end moving, like this. I'll show you the base movement. I'll place a sensor here. Wait. Okay, it should be here. You'll see the beam end move, as commanded. and the beam oscillates with respect to this excitation. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.